Welcome back, everyone. And in this video, we quickly want to discuss the concept of vectors and how we can measure if vectors are similar to each other. Because more or less among all the methods we're using, there will be some vectorized representation of the textual information. Okay, we already had this. For instance, no matter if we use the bag of word approach or the term frequency, inverse document frequency, we already have a vector representations of documents and words. Okay, because remember we had after we're doing this a matrix structure which looked similar to that one. So we have our rows each representing a document, and we have n documents, and we have each column representing a word. So we had d words, so the distinct words in our lexicon. And if we take a look at the rows, then we have more or less a vector of dimension d. So each element in the vector representing a number of the occurrences of the word in the document. And if we take a look at the columns, we have vector representations for a word. So for instance here for the first word we have an n-dimensional vector representation giving us the information for each element how many times this word occurs in the document. Okay, so we have more or less unique identifiers of words and documents given in vector form here. And for instance, this can be helpful. Let's say we have a target task behind this. So we have, for instance, here a target, and each document representing a review on Netflix or an IMDb or an Amazon. And the target variable would be, for instance, the rating of the movie or the rating of the series or the TV show, or for instance, a rating of a product on Amazon. And assuming that, for instance, a similar amount of certain words, positive words, or words suggesting or indicating a certain usability or whatever, it's very likely that the documents are similar, and this also leads to a similar rating. Okay, and basically this is what the machine learning algorithm would learn if we use the input information given on the left side in order to predict the target variable. Okay, so that is why it is helpful to check out the similarity of documents and words. And also furthermore, later when we're using models which try to also find out about the semantic meaning, for instance, of certain words in the text, then we want to measure if words that are similar to each other with respect to their semantic meaning also have word vectors which are similar to each other. Okay, so that is why we need the concept of similarity for vectors and to understand it. So I think from school, maybe you have in mind something like this. So at least in school, one starts typically, I would say, with the vectors representation in 2 dimensions. So for instance, we may have a vector here of this, which is represented by this point, and usually we draw an arrow to represent a vector in the 2-dimensional space. And for instance, now if we have another one, then it may look like this. Okay, but each vector here in 2 dimensions would be represented, for instance, by 2 coordinates, one that gives us the number on the x-axis and the other on the y-axis, for instance. So let's say the first vector is 1 and 1, and the second vector is, let's say, 3 and 1. Then if we want to find out if they are similar to each other, it means in the 2-dimensional space, for instance, we can picture similarity is how close the points are to each other. And if we want to calculate how close the points are to each other, okay, let's say let's draw another point here, and let's say it's this one here, or maybe let's say it's this one. Then obviously, for instance, the first point and the third point are probably a little closer to each other than the first point and the second point. Okay, and if we want to quantify this with a single number, then what we can do is we can calculate the distance between those 2 points, and that would be called the Euclidean distance. Okay, and the Euclidean distance is typically is typically quantified by first calculating that distance here and this distance here, and I guess you know the formula that we're using here. So we have c squared is equal to a squared plus b squared. So c is the square root of a squared plus b squared. So what the Euclidean distance does, let's assume that we have our third vector, which is called z, and it's 1 and 3. Okay, or it's not exactly 1 and 3. Let's say it's 0.5 and 3. Then what it does, it's in an element-wise perspective. It would calculate first the difference of 1 minus 0.5. So that is the blue line, right? And then we need the square value out of it plus the purple line, which would be 1 minus 3 and the squared value of it. Okay, so that's represented by the purple line. Obviously the purple line here is not exactly the length of the squared values here, or it is, it is basically not. No, it's not. And it's then in order to really calculate the value of the green line, we need the square root of the sum of these squared deviations. Okay, and this is how we would calculate the distance between the points, and we would say that the points that are more similar to each other, so the points that are more close to each other in the vector space, are the ones that are more similar to each other. Okay, so that is how we could identify documents or words that are more or less similar to each other. But sometimes, especially if you have high dimensional vectors, Euclidean distance can cause problems. So it is more common to use the concept of cosine similarity. And so what we do is we measure the angle between two vectors. So for instance, between the first and the second one would be that one here. So let's call it alpha, and let's call like this one beta. So in order to calculate the similarity between the vectors 1 and 3 and the similarity between the vectors 1 and 2, then we would, for instance, calculate the cosine of beta in order to calculate the similarity between the vector x and z. Okay, and the cosine of beta can be calculated by the dot product of those two vectors and divided by the L2 norm. So basically we need to write it like this. And also I need to quickly take a look at the formula, not to mess anything up. So it's given here in the slides. Here, for instance, we have it, or also it's also given on Wikipedia. So, okay, those are what's meant by it. And it's the product again. Okay, so let me just quickly go back to the iPad. So as you can see, it's the product. So on an element-wise level, we calculate x and z And here, let's say we have a dimension of d, for instance. So that would be like how our document vectors, the dimensions here of our document vectors. And here we have the sum over all the elements in each vector with a squared value and the square root of it again. Okay, so but this is just math, and it's just how we can, one possibility how the cosine can be calculated. Okay, but what is it? Again, I mean, this is basic math, but maybe it's also a long time ago for you when you heard this the last time. So let's say we have our unit circle. So let's say that's a value of 1 that we have here. So for instance, if we're taking a look at this angle here, and let's say that is beta, then the cosine would be the relation of this line towards this line. Okay, so the cosine of beta would be, let's do it again with colors, the relation of the purple line to the blue line. Okay, so whatever that line here is, or its length at the moment, it's the purple line, and divided by the length of the blue line, and that is 1 here, and that is the cosine. So that's why when we have you know, the sharper the angle gets here, the higher the cosine is. Okay, because take a look here, let's just delete this. Sorry. So let's say we would have an angle like this, then what we always need here is our 90-degree triangle, and obviously when we have a sharper angle, the length here is longer, and assume we have a not so sharp angle here, then obviously, as we always need our 90-degree triangle here, the length here is way more shorter, and shorter means that the cosine will be shorter, right? And also, I mean, this is a circle, so it goes around like this. So that means in our most extreme case for an angle of 0, then we would have a length of 1 divided by length of 1, so meaning the cosine is equal to 1. Now, for instance, if we go over, if we have a larger angle, so for instance, something like this, okay, so the overall angle is that one here, but the cosine now is the length that we have here, and obviously it has a negative sign. So it's somewhere between -1 and 1, okay? Because I hope you can see this. Basically, if we assume we always have a unit circle, but this can be calculated now for any other circle, but here it's the easiest one because we have always a value of 1 for what's given below here. And so again, let me just, if we have this kind of circle here, and a system of coordinates here. So starting here, we have very large and positive values, and this length is always equal to the cosine when we have a unit circle. Now, if we're going up here, it is still a positive number. If we go down here, the length here, but the length is getting shorter, so the cosine is getting less. And now if we have a larger angle, we have here a negative value going here to the left. Okay, and if you're in the number line, you have a negative value. And in our most extreme case, then we are here. So we have a value of -1 divided by 1. And then we go over here. And again, what we would have is something like this. And still a negative value, but it's getting, like, in absolute terms smaller. And then if you go over here, it's again getting positive, and the more sharp the angle gets, we were approaching 1 again. Okay, so that is why the cosine similarity will be between -1 and 1, at least if we have like vectors that whose elements are all real valued numbers. Okay, sometimes, for instance, for the bag of words approach, or also the term frequency inverse document frequency approach, can be it's only between 1 and 0 and 1 typically. So sorry that I this kind of was a little bit more detailed than planned, but this is like what a cosine is, and I think it's if you picture it like this, okay? Assume again we have certain vectors in the like two-dimensional vectors, and each vector representing, for instance, a word or maybe also a document. So like if we have our coordinate system here, it looks like this. And in very extreme cases, for instance, like one document has like is somewhere here, so only has like a certain number from one word, and for instance, the other document has only a certain number of the other word, then it would look like this. Okay, so for instance, X would be, I don't know, it had 10 occurrences of the first word, but 0 occurrences of the other word. And the second document, second vector, would be something like this. Then it would be kind of look like this. Okay, so obviously if we have a document only with the one word and the other document of the other word, the documents do not have anything in common. So you know, the vectors that are given here, so this and that one, they are, you know, have an angle between of 90 degrees. And the cosine similarity would be 0. Okay, you can see that because if you calculate the dot product here, then we have 10 times 0 plus 0 times 10. So 0 plus 0 is 0. So also the cosine similarity will be 0. Okay, because this is what we would calculate if we want to you know, calculate this number that we see above here. And so graphically speaking, if they do not have anything in common, then they have like they're standing on to each other with a 90-degree angle. And later, if we have like, I mean, if we picture with the number of words, then there will be no negative numbers. But later we will face models which also have word vector representations that have negative values. So for instance, assume now a very extreme vector with -10 and 0. So that would be like just pointing the same with the same length, but in the opposite direction. So this is if it's not only independent of each other. So this is would be the information. The information would not be here that that this vector and this vector do not share anything together. This would be the information that they are behaving quite in the opposite. So in the one document we have 10 words here and 10 occurrences, and the other word document would have -10 occurrences. Even that doesn't make sense here. Okay, so meaning Euclidean cosine similarity of 0 is more or less like independence, or it's not more or less, it is basically mathematical independence of vectors. So they do not share anything. Okay, they have no similarities. There's nothing similar between them. So knowing something about the first vector doesn't provide any idea or any information about the second vector. When we have similarity, if it's very positive similarity, we know that the two vectors are quite similar to each other, meaning like knowing about the first vector gives us already an idea how the other vector is going to look like. When we have a negative value of the similarity, that's also very informative, because if we know the blue vector, we almost know that the purple vector looks more or less like the same, but in completely opposite direction, okay? So that's just also important to understand, okay? So that's like the concept of similarity on the vectors here. And I think it was important at this point in time to discuss this because in the future, no matter if you use the LSA or the LDA method, or now word vectors like word2vec or Glovi, or document vectors like doc2vec, we always have a vector representation either sometimes of words and sometimes of the document, okay? So and typically we will quantify the similarity by the cosine similarity measure, because it's more more common to use that one when we using the similarity of word vectors or something, because typically they are rather high dimensional, okay? And that is why we use the cosine similarity. Sometimes, for instance, like in case of the LDA method, where we typically have a certain number of components and representing a document, it may also be okay or helpful to use the Euclidean distance. All right, so that's like I would say the fundamental knowledge regarding the similarity of vectors I wanted to share upfront before we now in the next video dig deeper into our first topic, modeling, and where we'll discuss the LSA method. Okay, so see you in the next video. Bye bye.